welcome to the second part about Laplace transforms. In the previous part, we basically went through a sort of backwards route to inventing the Laplace transform. And now let's first recap what we got and then compute it for a few functions. So first of all, we ended up at the definition that the Laplace transform of a function f is a function taking s into the integral from 0 to, well, it should say infinity here, so let's correct that at once. 0 to infinity of the function f scaled by an exponentially decreasing function, where the factor s is the parameter here. So for each s, it will be one value of the integral, and all those values together sort of represent f. It's a completely different view of f. And this is for functions f which vanish as x goes to infinity. Okay, and then we also found out that there is a law which lets us transform derivatives into multiplication and addition of a constant. And that's the key to their usefulness in solving ordinary differential equations. And we claim, but haven't proved, but it's a good exercise, that L is a linear transformation from the vector space of real functions to the vector space of complex functions. And then we also, using that, we introduced a little helper function gs, which is just a version of the exponential function with the factor minus s in front of t. Okay, let's try to compute the Laplace transform for some example vectors, the exponential, sine, and cosine. And we do that by using the law, the Laplace derivative law, and when we have an ordinary differential equation specification. So here we got a specification of the exponential function, saying it actually is invariant with respect to derivative. It ignores it, it just returns the same. And if we apply it at the point 0, we get 1 out. And those two things we need to know to be able to transform it. So then let's state the LD law, the Laplace derivative law. We get here the L of derivative of x at s is equal to minus x of 0 plus s times the Laplace of x without the derivative of s. So this was just this law where f has been replaced by x. Okay, the next step in these operations is to use the ordinary differential equation or the specification of x. So it means we can compute this part to 1 and this part to x. So we write the second line with the same equation but simplified a bit. L of x and s equals minus 1 plus s times, well, unchanged L of x of s. I should perhaps remind you here that I'm using Haskell notation for application. So this is the L operator applied to x, applied to s. The exp function is not applied to s. The L is applied to exp, and internally it uses s as a subscript to this g function, which is actually an exponential. So here is where s is used. So the s argument goes all the way into the Laplace definition and up in the exponent inside the integral. Okay, now we have an equation where we see the same expression twice, L exp s, L exp s. So if we would call that, say, x or y or something like that, we can just solve for that value. And let's use the standard notation here that when we transform a certain function, we use a capital version of it. So I will here call exp capital E. So let's use E for the function L applied to exp. Notice here the type of E, it is a complex to complex function. So it's a Laplace transform hungry for an S and returning the value of this integral. Okay, as I said, let's first take this step, then we introduce the E of S equals -1 plus S times E of S. And then let's collect the values. So we have actually 1 minus S times E of S equals -1. I just moved this term over to the other side. And that's the minus S times E of S here. And then I divide by 1 minus S, giving me E of S, the function E of applied to S, is equal to -1 over 1 minus S, or equivalently 1 over S minus 1. Okay, so what have I proven here? I've shown that starting from the specification of exp and the LD law, the Laplace derivative law, I've computed the Laplace transform, and I can record it here, that the Laplace transform of exp at S is equal to 1 over S minus 1. So if S is equal to 2, for example, it's 1 over 2 minus 1, which is 1 over 1, which is 1, and so on. It's also worth noting that it's not defined for S equals 1, because then this would go to infinity. So basically this function that we transform exp2 is only usable for the real part of S greater than 1. Remember, I was saying that a requirement on the functions here is that the function should not grow too quickly. And another way of solving that is making sure that S is sufficiently big, so that this exponential decay is sufficiently fast. Okay, this was deriving the Laplace transform expression for exp. Notice that we've gone from one expression, an exponential function, to what we could say is a much simpler equation. I mean, it's a quotient, but it's just a quotient between 1 and a first order polynomial. So that's rather easy to compute with. Okay, let's generalize a little bit. Let's go to the exponential with a factor in front of t. So the previous one was just g minus 1. So we have that example. Let's write it in the corner here. So g of minus 1 is actually exp. So exp that we had before is a special case of this function, but here we can do it for a wider class of functions. So first, to use the LD law, which we have copied up here, we have to have an ODE specification of G alpha. But we computed one already earlier. We know that G alpha's derivative is the scaling by minus alpha of G alpha. So the function G alpha is such that when we take the derivative, we basically get back the same thing, but multiplied by a constant, minus alpha. And we also computed earlier that G alpha at 0 is 1 for every alpha. Okay, that's our ordinary differential equation. And then to go the same way as we did in the previous Jamboard slide, we again write down the LD law, Laplace derivative law, for this G alpha. So the LD law gives us that Laplace of derivative of G alpha at S is equal to minus G alpha at 0 plus S times L L G alpha S. Now we use the equations we've got. These equations, the computation of the derivative and the computation of the value at 0. So the value at 0, let's do that first. Minus G alpha at 0 is -1, just as before. And then the other side here, we get L of scale minus alpha G alpha. Oh, I shouldn't have written the -1 first. Okay, there's too little space. So L of scale minus alpha of G alpha, n parenthesis S equals -1 plus S times L G alpha S. And now scaling inside the Laplace transform, that's useful to prove separately, is just multiplication outside. So it's linear. So we get here minus alpha times the Laplace transform of G alpha at S. And still the right hand side is the same. And now if I use exactly the same style as before, I should introduce a name. Let's capital G alpha be the Laplace transform of little g alpha. That means I can simplify this expression slightly. So minus alpha times capital G alpha at S is equal to -1 plus S times capital G alpha at S. And then I collect the terms. So here we get minus, well, let's extract the minus sign. Minus alpha minus S times G alpha of S equals -1. Where I've just moved this term over to the other side. Oops, sorry, it was minus alpha plus S. I extracted the minus sign from alpha and the minus sign I get from plus S when I move it to the other side. Now I can get rid of the minus signs on both sides and divide by alpha plus S, which gives me at the end that G alpha of S is equal to 1 over S plus alpha. So what have we learned? We've learned that the Laplace transform of G alpha at S is equal to 1 over S plus alpha. And as we know the definition of G alpha, being this one, we can use this to express it in the more well-known form. So the Laplace transform of the function e to the power of, let's use beta S. Notice I've now not used minus. So I use, instead of minus alpha, I use beta. And that at S is then 1 over S minus beta. So beta is minus alpha, so that's why it becomes this case. So let's try to remind ourselves, is this compatible with the previous slide? Where we said the exponential function was 1 over S minus 1. And that's fine because the beta here, so the special case, we can write up again to remember it. The special case where we had lambda x arrow e, oh, there was beta s, I should have written beta t, sorry about that. The s is not even bound there, so it can't be s. So lambda t e to the power of t, so basically beta is equal to 1, then it's 1 over s minus 1. So that's just a special case. Okay, so that was reassuring. Now let's move to a slightly more interesting example, the Laplace transform for sine and cosine. So the previous examples, it would have been pretty easy to actually directly do the integration here, because e to the power of x, or e to the power of t, or e to the power of alpha t and so on for the exponential would have been simplified. It would have been simple to compute the integral. When we multiply the exponential with sine or cosine, it's not so obvious anymore, but then it's really this LD law, the Laplace derivative law, really shines. So let's use that. But to use it, we need to start from the ordinary differential equation specification of sine and cosine. So we need to know what is the derivative of sine, what is the derivative of cosine, and what is sine at 0, and what is cosine at 0. Well, sine at 0 is 0, cosine at 0 is 1, and the derivative of sine is cosine, and the derivative of cosine is minus sine. Notice that all of these are now point-free. These parts are point-free. We take the vector sine, the whole function. So at each index, it's the sine of that index. And then we return the whole function cosine. Okay, so if we start from this specification and then move on to actually, which I sort of summarized up here, move on to try to compute now the Laplace transform using this technique of the LD law, which I've abbreviated here using the prime instead of the D, but it's still the Laplace derivative law. So what I'm doing in all of these cases, I start of writing down the LD law for our special functions. So in this case, twice, one for sine and one for cosine. So this is then the Laplace of sine prime at S is equal to minus sine of 0 plus S times Laplace of sine at S, and the Laplace of cosine prime at S is minus cosine at 0 plus S times L of cosine at S. And then I use the ordinary differential equations. Well, maybe I should make the same kind of a blue bracket here, saying these two come together, and they come from the LD law. Now I use the specifications to rewrite using these 4 pieces of knowledge, so that we get here the next step, the Laplace of the cosine of S equals, well, that's a 0 plus S, well, I don't even have to write the plus here, let's just shorten it. L of cosine is just equal to S times L of sine of S, and the other one becomes L of minus sine of S equals minus 1 plus S times L of cosine of S. Okay, at this stage it's useful to introduce these shorter names. So I will introduce here capital C for Laplace of the cosine and capital S for the Laplace of sine. These are functions from S. Okay, this is also a bracket. Sorry. So now I should try to rename the places where L is used by this capital C and S so that we recognize where we are at. So I'll just copy down. This is the cosine transform of S should be equal to S times the sine transform of S. And minus, I'm using the linearity of Laplace here, so minus the sine transform of S equals minus 1 plus S times the cosine transform of S. Okay, nice. I'm step by step getting simpler and simpler equations. And now, if you notice that this equation is particularly simple, I will just expand this one into here. So this I can write one more step. It's minus 1 plus s times s times s of s, capital S of s. So it's just minus 1 plus s squared times capital S of s. So now we have an equation for capital S of s, so the transform of sine. Let's simplify it one step further. We can keep the cosine as well, actually. Cosine equals sine times S of s. And the sign, we're collecting the terms here. So if I'm starting from the other side, we got s squared, s, and then we add another 1 times s of s, s of s equals, so notice what I did, I took this term and I added this one. So I got s squared plus 1 s of s. So that's on this side, and then moving the minus 1 over to the other side and swapping it around. So that's equal to just 1. Okay, and then we can now extract s. So let's swap the order. S of s is actually equal to 1 over 1 plus s squared, or s squared plus 1, whichever you want. And the cosine is just s times that. So s divided by 1 plus s squared. So to sum up, from the specification of sine and cosine, actually mutually recursive specification, because one is defined in terms of the other, which is defined in terms of the first. The specification and the LD law, together with some linearity, which are written here in a more general form than before. This combined gave me expressions for the sine transform and the cosine transform, and we sum up that in the box as we usually done, that the Laplace transform of sine at s is 1 over 1 plus s squared, and the Laplace transform of cosine at s is s over 1 plus s squared. Okay, and as before, I mean, if we want to, yeah, okay, I've got them up here. So together now, what we've sort of computed during this session are the Laplace transforms of exponential with the factor. We have the LD law, we have linearity, and then we have two more cases, sine and cosine. And as you might imagine, it's not difficult to extend this to compute correspondingly if there is an alpha. If there is a sine of alpha t or a cosine of alpha t, then you get slightly modified equations here with an alpha square involved as well. Okay, but this was all for this part. Let's take a break.